first thing I like to do is to actually hand out the questionnaire to find out more about you. And hand this out.
If you're just auditing the class, don't take one.
And then the second thing I like to do is to actually hand out a rough course outline. And so that you can roughly see what we're going to teach. But I'm not bound to this thing. I'm not bound to this course outline. I did talk a little bit from Okay, first let's go through some miscellaneous things about the course that I'd like to tell you about myself and where you can find me. And my email is verification. Phone number is okay, and then Ian Liu is going to help me teach the course. He's also the chief TA for the course, so he will do some of the lectures as well as being a TA. So he's owning the system. What do you want to use a Gmail address? Or
Yes.
Gmail? Okay, it's Gmail AYL. You want to give phone number? No? Okay. And so there is a rough course outline. There will be 2 lectures per week. Since I travel a lot, I'd like to propose that we start the next lecture at 9 a.m. and then we'll teach half an hour more every lecture, and then after that we'll take a week or 2 off. Or maybe I plan to have the week before spring break off, so that we don't have to teach that week. I'll give you some term project or homework to do. And then, so next lecture, please come at 9 o'clock. Okay? The textbook I recommend for this course is actually by David Miller of Stanford. But I will also give a lecture note. Okay. And previous versions of the lecture notes are available on my website. You can go to my website and download them. Okay, and I suppose Ian will help me improve this lecture notes in the future. Okay, presently they have been written by me. And I usually update them every semester. By the end of the semester, you get a new version. I suggest that you read the lecture notes first, because I'm going to lecture quite closely in accordance with the lecture notes, and then use the Miller's book as a reference. Because I find that, or at least most students told me that the lecture notes are easier to read. Okay, you can read the lecture notes first. And there is another book for reference, I think, on quantum transport that you might find interesting to read. It has by Superior Data of Purdue University. I don't remember the full name now. I think the full name is on the website. And there are sections of that book that I find very easy to read. That book is for both undergraduate and graduate. And in the beginning of the book will tell you which part is undergraduate, which part is graduate. I find that the undergraduate part is actually quite easy to read, and you can read the. So this is for UG and grad. Okay, you can also use that as a reference. So this would be a reference text as well. Okay, let's see where we can go from here. You are here because you're interested in quantum mechanics and quantum physics. So there's chapter 1, the introduction of my lecture notes, where we talk about why we want to study quantum mechanics. Well, quantum mechanics are very important. Actually, it was first motivated by chemistry. The chemists were making very interesting observations on optical spectroscopy of atoms and molecules, and there were things that they could not explain. And in chemistry, they used to think that if you have a nucleus, there is a particle called an electron that moves around the nucleus. And they did not know how the electron moves around the nucleus. So they had very simple-minded model, as if this is like a moon around the Earth, or maybe like the Earth around the sun. They just used a classical mechanical model to try to predict how these things work. But it never worked out really well. Okay, so they had things called Ribert atoms in the very beginning, which are only a simple model for atoms, and those models really never work. So it was not until Schrödinger, I guess it was about 19, I have it in my lecture notes. 1925. Then he came up with this Schrödinger equation. Okay. That essentially is equivalent to a wave equation. And he postulated, together with many other physicists, that electrons should be thought of as a wave rather than just a particle. And because of that, he was able to predict a lot of the absorption lines in atoms, because if you think of it as a wave, it's like a microwave cavity. The atom would behave like a microwave cavity, and it would have absorption lines, resonance lines, and so on. And that was a breakthrough. Okay, we will talk more about that later on. But it was because of chemistry that we had all this important discovery, and this discovery essentially impact other parts of human technologies. Okay, so if you just look at things like quantum mechanics, and what you can explain is important for material science, optics, electronics, and so on, and even quantum information. You probably hear about that recently, that you can use quantum mechanics to encrypt things so that you have quantum cryptography. Okay, and there are other things like insulators and conductors. How do you explain the behaviors of insulators and conductors? in semiconductors, and also more recently, the behavior of giant magnetoresistance. Okay, this is rather new. It's called GMR, and that could only be explained if you understand quantum mechanics, and you have things like quantum optics. Quantum optics is essentially the combination of quantum mechanics with electromagnetics. And it turns out that if you learn how to incorporate quantum mechanics into electromagnetics, you can have a quantized form of electromagnetics called quantum electrodynamics. Where you combine both quantum mechanics and electromagnetics. And in the optics field, they like to call this quantum optics, and you can also call this quantum electromagnetics in the microwave field. Okay, so there are things that come from, because of this quantum information, because of quantum mechanics and quantum information, so you have things like QCs, okay, lots of QCs, quantum computing, quantum communication, and then you have things like quantum cryptography. So there are 3 QCs, cryptography, that you can think of because of quantum mechanics. Okay? So you can read about it in my lecture notes. I give very many examples, and of course one of the more recent things that is of interest is Casimir force. And Casimir force is actually due to some force which comes from vacuum. It turns out that after this course, if people ask you what is vacuum, and before this course you will say vacuum is nothing, there's nothing there. After this course, you'll learn that in vacuum there's something. Okay, even though there's nothing, there's something, and there's something called the vacuum fluctuation. Of electromagnetic field. So if you have 2 parallel plates, and you put this in vacuum and there's at 0 temperature, 0 degree Kelvin, so supposedly there's nothing, everything is frozen down to the very bottom energy state, but there's still something there. There's an electromagnetic fluctuation in there. And this electromagnetic fluctuation can pull these 2 parallel plates together. And you can show that because of them, these 2 parallel plates would want to snap to each other. Okay, there is a force that's got them to snap to each other even if you put this in vacuum. So this is very important for NEMs and MEMS. We want to make NEMs and MEMS, and let me tell you what this acronym stands for. This is nano electromechanical system. Okay, this is just micro. Before that it was micro, and now it's nano. NEMs and MEMS are also quite important for engineering, even though if you're a microwave engineer. The reason why they're important is because acoustic wave has a much slower velocity than light. So if you make an acoustic cavity, say if you wanted to make a resonator at 3 gigahertz, you can make the cavity very, very small. But what is microwave? What is electromagnetic wave at 3 gigahertz? Does anybody remember the wavelength? What?
It's in the meters.
In meters? I always remember 10 gigahertz, 3 centimeters. 1 gigahertz, 30 centimeters. So 3 gigahertz is 10 centimeters. So not in the meter range, but that size. So if you want a resonator like a computer has a clock rate of 3 gigahertz. So the microwave, the electromagnetic wavelength inside your computer now is about that big, maybe 10 centimeters is about that big. So if you want to make a resonator, cavity resonator, do you remember how big your cavity resonator has to be in order for an electromagnetic mode to fit inside? What is the minimum wavelength that you could have? It's about half a wavelength, right? You need at least half a wavelength for an electromagnetic wave to fit inside a microwave cavity, which means that your microwave cavity has to be at least this size, at 3 gigahertz. That's not very small in terms of nanotechnology. Okay, we want to make things a lot smaller. So how can we make things a lot smaller? We go through acoustic, okay, or elastic. And in this kind of wave, they travel a lot more slowly. If a wave has a very slow velocity, its wavelength is a lot shorter. Hence, you can make acoustic resonators that are much, much smaller than microwave resonators. So you can down convert to acoustic wave, make a resonator. Resonators are important in microwave circuitry because they act as filters, and band pass and band stop filters and so on. And then you can convert back to electromagnetic signal, and hence use this kind of technology to miniaturize your microwave circuits and so on. Okay. Are there any questions so far? Okay, these are all the different kinds of things you can apply to in using your knowledge of quantum mechanics. But quantum mechanics is actually quite bizarre, okay? And it's very bizarre because it has to be related to something that you're not dealing with in your everyday life. In your everyday life, we deal with classical mechanics. We know how things work because we can predict how things are. But in the quantum, in the microscopic and nanoscopic world, there are a different set of laws. Those laws are not experienced by you and I in our everyday life. So we have to be imaginative and open-minded when you learn quantum mechanics. You have to go to a world where you have not experienced before. Okay, so it could be very bizarre. But it is a great intellectual achievement in the 20th century because, as one physicist says it, you really do not know what the laws are at the microscopic and nanoscopic level. So you observe experimental outcomes. And with the experimental outcomes, you conjecture what the law should be. So it's like watching two chess players playing a game of chess. And they move about, and you really don't know what the rules are for the chess game. But maybe after watching a long time, figure out what the rules are. Okay, it's that kind of difficulty that physicists and scientists have to go through to figure out what the laws of physics are at the very, very bottom level. But one of the most difficult things about quantum mechanics is probabilistic interpretation. Okay, the probabilistic interpretation says that if you have an electron going around a nucleus, in our everyday life we know where the electron is. Is it here? The electron is there. Okay, but in quantum mechanics, you do not have the kind of interpretation. The electron is everywhere. Okay, electron is everywhere, and it's only described by a wave function. You do not know where the electron is until you do a measurement. Okay, before you do the measurement, you have to assume that the electron is everywhere. After you have done the measurement, you have pinpointed where the electron is. Then you can say, I found an electron at that position. Okay, so quantum mechanics has this kind of interpretation that you do not know where things are. before you measure them, you do not know what state the system is until you perform the measurement. And after the measurement, you know what it is. And so there is a kind of a wave function to describe, say, the location of the electron. But this wave function says that the electron is everywhere. And then if you take the amplitude square, this becomes a probability density function. And this function describes the probability density of your scope of finding an electron. If the wave function is very strong, that means that there's high likelihood of you finding an electron there. And if the wave function is very weak, you have a very small likelihood of finding an electron there. And it is this kind of interpretation that bothered physicists a lot. Okay, it bothered physicists even like Einstein. He said, God doesn't play dice. So he made the same famous saying. Okay, because if you agree with the probabilistic interpretation, you essentially have to agree with the fact that you do not know where things are. Okay, you only know where things are after you've done the measurement. Einstein did not like that. Say that we must have known what things. Like he asked a very famous question: is the moon there if you don't look at it? Okay, according to quantum interpretation, you do not know if the moon is there if you don't look at it. Okay, and of course, according to our classical understanding, the moon is always there even if you don't look at it. Okay, so Einstein felt very uncomfortable with this kind of interpretation, but he regretted it, I think, finally. Okay, the quantum world is kind of strange, bizarre. That if you don't know and don't perform a measurement, you really don't know what things are. Okay. So, at the quantum level, you actually have to learn how to use wave to describe a particle rather than just classical mechanics. If you want to understand the behavior of an electron around the nucleus, it has to be described by a wave function. Okay? And it cannot be regarded as a particle. Okay, so we have this wave particle duality thing that we actually have to think of particles as wave and wave as particle. And that has been observed many times over in our understanding of the universe. The first encounter of this wave-particle duality is actually with electromagnetic wave in the realm of photons. Photons actually are related to EM wave. Okay. At one time, people thought that optics and electromagnetics are two separate fields. Okay. Optics were done in the 1700s. There were people like Snell and all those people, they were actually coming up with laws for optics. And electromagnetics were done in the 1800s. There were people like Amperes and Faraday, and people who even invented machineries in the early 1800s, electrical machineries like motors. Telegraphics, okay, was invented in the 1800s. It was not until 1864 that we have James Clerk Maxwell. Who actually came up with a set of equations. Of course, he used knowledge from his predecessors, like Amperes and Faradays and Gauss. He completed Maxwell's equations, I would say. And those Maxwell's equations that he completed actually bridge the gap between optics and electromagnetics. And both of them travel at the speed of light. You know, c is what? Humongous number, right? 3 times 10 to the 8 or something meters per second. What is the number for c?
Let's use 3 times 10 to the 8
meters per second. And he can show from his equations that both microwave, electromagnetic wave, and radio wave, as well as optics, travel at this humongous speed. Okay, and finally we concluded that these two must be the same phenomenon, coming from the same set of equations. But then there was actually in 1864 in optics, back in very early days, I noted that in even 1717, okay, Newton was able to show that light wave is a wave by doing an experiment called the phenomenon of Newton rings. I think he was able to put a glass, something like this, another piece of mirror, and then you shine light on top of it. He sees the interference pattern that he sees on this top part of the thing, and then he said, if light had not been a wave, I wouldn't be able to see those rings. So back in 1717, he concluded that light was a wave. But then about 1905, we had Einstein who came along and showed the photoelectric effect. Okay, we showed that photons or optical waves, in addition to being a wave, display the effect of a particle where the energy exists as a packet of energy. Okay, exists as packets of energy. And that packets are of this order. Okay, so the energy comes in packets. So they thought, in that case, light must be a particle as well. So we came up with this wave-particle duality. I would like to say that in 1900s, there was a Planck, there's another guy, Planck. He actually was trying to fit experimental data to a radiation law, and he couldn't fit the data unless he assumed that the energy of photons were of this form. And he also gave the initial clue that photons must exist as packets of energy because he has a cavity. He finds that you can find modes inside. In addition to being modes, the energy that you can measure those modes in are measured in terms of this packet. And if it does so, it comes up with this Planck radiation law that predicted what he observed in the universe. And that was before him, there was this Rayleigh-Jeans law, which was kind of old-fashioned. Okay, this law superseded Rayleigh-Jeans law that has no quantum mechanics in no QM. And this law actually has quantum mechanics because of the assumption of E is equal to h bar omega. Okay? And then 1905, we have this thing, E is equal to h bar omega. And then people started to think that a wave can be a particle as well, like a photoelectromagnetic wave. Then what about electrons? Maybe an electron should be thought of as a wave as well, instead of just being a particle. So it was around, let me see, it was around 1924. It's Franklin, Probabilistic. Thought that electrons should be a wave, and then you can have a wavelength associated with each electron, and that wavelength is given by this formula, where h is called a Planck constant because Planck actually guessed this formula long ago, way before we understood quantum mechanics. So that constant is named after Planck, and Planck constant is equal to 6.626 times 10 to the minus 34 joules second. So we have half an hour more.
We have 50 minutes.
Okay. Okay, so he came up with this Planck constant that allowed him to predict this Planck radiation law. And then de Broglie looked at this information that had been around and decided that electrons should also have a wavelength. And maybe electrons also can be like photons, behave like a wave as well as a particle. And he actually get this fact from the fact that E is equal to h bar omega, but an energy of a photon is also given by Pc. Okay, and that came about, this knowledge comes from special relativity. Special relativity is about 1905, I believe, by Einstein. Einstein predicted a number of things. One of the things he predicted was the universality of the velocity of light. Like this has to be always equal to each other, irrespective of what coordinate system you are in. And if you go to a different coordinate system, this has to be always true. So time and space can be different in different inertial frame. You can read about special relativity if you want to, but C never changes. C is the velocity of light, which is a universal constant. And together with special relativity, it also predicted things like E squared minus P squared C squared N0 C squared squared. Okay? Like momentum and energy are related to each other just like time and space. Okay, this is part of the output of special relativity, where P is the momentum of the particle, M0 is its rest mass, C is the velocity of light. But for a photon, there's no mass. Okay, for a photon, there's no mass. So special relativity predicted that for photons, E is just equal to Pc. And de Broglie make use of this fact. If you make use of this fact, then you can see that omega is equal to 2 pi f, and f is c over lambda, right? Or c over lambda. F is c over lambda. So you can see that h bar omega is actually equal to, let me see, would be equal to 2 pi c over lambda times h bar. But h bar is defined to be h over 2 pi. So you can come up with de Broglie's formula if you go through this manipulation. Okay, h bar is sometimes called the Dirac constant. Dirac is also another very famous physicist. So it's called a reduced time constant. Dirac was essentially the guy who came up with quantum electrodynamics. Okay, this is due to Dirac. Okay. So with that kind of mindset, the fact that experimental data could not be explained, you have to make an electron into a wave. That was the mindset of the physicists during that period. Then what equation should the electron satisfy then? Okay. So then came Schrödinger. Schrödinger in 1925, I believe, presented his Schrödinger equation. And in 1926, it was published. So 1925, as I say here. 1926, Schrödinger equation was published, and the electron should be thought of as a wave, and then he wrote down Schrödinger equation. And if you motivate Schrödinger equation, you can motivate it somewhat this manner. We say that, say if we just have a plane wave, and all of you know what plane wave is. If you were to use this kind of plane wave, as you have learned in ECE487, it describes a microwave. It also describes an optical field, but can it be used to describe an electron when it behaves like a wave? Okay. So if that is the case, then if you look at wave equation, this should be equal to minus k squared psi z. Okay. And I can generalize this to a three-dimensional wave function. In 3 dimensions, as you have learned from your ECE487, This r is x, y, z. It's minus k squared psi. Do I need to show you this, or all of you know this from your 350? You're comfortable with this, right? No need to show. Okay, very good. So then k is equal to 2 pi over lambda. And you can say that h bar k is equal to p. Okay? If you can associate p is equal to h bar k, if you go through this, from the Broglie's formula, you can show that p is equal to h over lambda, okay, which is equal to h over 2 pi times 2 pi over lambda, which is equal to h bar k. Okay, so this follows from the Broglie's formula. And you can actually rewrite this equation in a more suggestive fashion and say that if I multiply by h squared, then this equation becomes this minus h squared k squared psi of r. The wave equation becomes something of this nature, but h squared k squared is just p squared, or the momentum squared. Okay. So this Laplacian operator is proportional to momentum squared. It seems to indicate some kind of velocity square, because momentum squared is proportional to velocity squared. So Schrödinger came by and said that h squared Laplacian squared over 2m psi of r, since this is equal to h squared k squared over 2m psi, this is like p squared over 2m. This is somewhat like some kind of a kinetic energy. So if you write the part of the wave equation in that manner, that